Hi friends, today we will discuss about Maxwell Boltzmann statistics. This is actually classical statistics in which particles are distinguishable and there is no limit on the number of particles in any energy level. So it is applied to distinguishable particle and the conditions are particles are distinguishable from each other. Each cell may contain 0, 1 to Ni particle. Total number of particles of system remain constant. It means N is constant. Sum of energies of all the particles in the different groups taken together, that is total energy of the system remain constant. So E equals to constant. So particles are distinguishable. There is no limit on the number of particles. Total number of particles remain constant and total energy of the system remain constant. Now we consider a system of n distinguishable particles. These particles be divided into groups or levels such that the energy levels E1, E2, Ei may contain N1, N2, Ni number of particles and the degeneracies in these levels are G1, G2, Gi and so on. Now these are energy levels. There are total I energy level and Gi sublevel with Gi minus 1 partitions are shown here. So consider a box, divide it into Gi sections, distribute Ni particles among them. The number of ways to distribute N1 particle in first state are, total number of particles are N and we are choosing N1 particles out of N. So this will be done by NC N1 ways, or this will be factorial N upon factorial N1 factorial N minus N1. Since N1 particles are accommodated here, so remaining N minus N1 particles are there and we want to choose N2 particles out of N minus N1 in second state, and this will be done by N minus N1 C N2, that is factorial N minus N1 upon factorial N2 factorial N minus N1 minus N2 continuously. For find total waste to distribution, we multiply all the previous factors. So factorial N upon factorial N1 factorial N minus N1 into factorial N minus N1 upon factorial N2 factorial N minus N1 minus N2 into and so on. This factorial N minus N1 and factorial N minus N1 will be cancelled out, and this factorial N minus N1 minus N2 will be cancelled by a term which we have here. So the result of this equation will be factorial N upon factorial N1 factorial N2 factorial Ni. First particle can be accommodated in any of the Gi group by Gi ways. Since there is no restriction on the number of particles, so second particle can be accommodated in Gi group by Gi ways, and in the same way, Ni particle can be accommodated in Gi group by Gi raised to Ni ways. So total Ni particle can be accommodated in Gi group by Gi raised to Ni ways. So total number of eigenstates for the whole system G is equal to factorial N upon factorial N2. G equals to factorial N upon factorial N1 factorial N2 factorial Ni into G1 raised to N1 G2 raised to N2 Gi raised to Ni, and this can be written as factorial N G1 raised to N1 upon factorial N1 into G2 raised to N2 upon factorial N2 into Gi raised to Ni upon factorial Ni. or G is equal to factorial n pi I Gi raised to Ni upon factorial Ni. This whole thing will be written in the form of pi. Now, according to the postulate of a priori probability of final state, the probability is given by omega is equal to factorial n pi I Gi raised to Ni upon factorial Ni into a constant k. And on taking the logarithmic of this equation, we get log omega is equal to log factorial n plus sigma I Ni log Gi minus log factorial Ni plus log k. Now from Stirling approximation, log factorial x is equal to x log x minus x. So this log factorial Ni will be replaced by Ni log Ni minus Ni. So this will be the result. This is total number of particles, and sigma Ni is also total number of particles. So n and n will be cancelled out. N log n is a constant and log k is constant. So n log n plus log k is replaced by a new constant. And hence we get log omega is equal to k1 minus sigma I Ni log Ni minus Ni log Gi. This k1 we put here in place of n log n plus log k. Now by differentiating this equation, delta log omega is equal to differentiation of k1 is 0 minus sigma I Ni as it is, differentiation of log Ni is 1 upon Ni delta Ni plus log Ni as it is, and differentiation of Ni is delta Ni. Now log G is constant, so it will remain here, and differentiation of Ni is delta Ni. This Ni and Ni is cancelled out, so here we have only delta Ni, and if we take delta Ni common from this equation, then we will get delta log omega is equal to minus sigma I log Ni upon Gi plus 1 delta Ni. For maximum probability, delta log omega is equal to 0. So sigma I log Ni upon Gi plus 1 delta Ni equals to 0. The other conditions are total number of particles remain same and total energy of the system remain constant. Now, if we differentiate these two equations, then delta n equals to 0 and delta E equals to 0. So these are the differentiation. This is our equation number 1, this is 2, and this is 3. So 1, 2, and 3. Now from Lagrange's method of undetermined multiplier, equation 1 remain same. Equation 2 is multiplied by mu and 3 by beta. And on doing all these things, we get sigma I log Ni upon Gi plus 1 plus mu plus beta Ei delta Ni equals to 0. But delta Ni is arbitrary, so log Ni upon Gi plus 1 plus mu plus beta Ei equals to 0. Here mu is a constant, 1 is also a constant, so 1 plus mu is replaced by another constant alpha. So this will be log Ni upon Gi plus alpha plus beta Ei equals to 0, or log Ni upon Gi equals to minus alpha plus beta Ei, or log Gi upon Ni is equal to alpha plus beta Ei. Now on taking the exponential on either side, we get Gi upon Ni is equal to exponential alpha plus beta Ei, or Ni is equal to Gi upon exponential alpha plus beta Ei. This is our Maxwell Boltzmann distribution law. Here we end our session. So for more interactive session of this kind, please like, share and subscribe the channel. Thanks for your kind patience. Goodbye.